Hi, and welcome to Chapter 7, Lesson 1, where we are going to be starting our little chapter on radioactivity. So today we have a little bit of an introduction, a reminder of what isotopes are, and a little look at radioactive decay. Next day we will look specifically at alpha, beta, and gamma decay. So today let's start with a little review. Here we have a little box that I have put the element oxygen. And this is how you see it on your periodic table. So when we look at it, we notice that it has an atomic number of 8. That's here at the top. And this is simply the number of protons. If it's a neutral atom, then the number of protons equals the number of electrons. If it's an ion, then the electrons are not the same as the protons. This oxygen also has a mass number of 16.0. Here's the mass number down here. And the mass is simply the number of protons plus the number of neutrons. We also know that an atom is stable when it has a full valence shell of electrons. So when the electrons in the outer shell either are shared or transferred, then that will create a more stable atom. And remember that only the electrons move. The protons do not move. And if the protons did move, we would be changing the atomic number here, so that would make it a different element. So only the electrons move. All right, into today, radioactivity. When we hear the word radioactive, or like that Simpsons episode, look out, radioactive man, we're usually thinking about negative effects, how things have changed negatively. Often with cancer, you can have that from too much exposure to radioactivity. Radioactivity can also, however, be used for good. It can be used to generate electricity. We can use it to help cure cancer, all these cool things for medical treatments. So a substance is said to be radioactive when changes occur to its nuclei. So right in the center, what's in the nucleus again? We have the protons and neutrons in the nucleus, and then all around are the electrons. So when changes occur inside the nucleus here, then it will release high energy particles and rays of energy. And when it does this, we call that radiation. So those are some terms that you should make sure you are familiar with. Here is a figure that you've seen before. In grade 8, you learned about visible light and you learned about the whole electromagnetic spectrum. Here on the left side of the spectrum, you have long wavelengths. So this is low energy, low frequency, and long wavelengths. So E stands for energy, F for frequency, and W for wavelengths when I write it there. And then as we move along from radio waves to microwaves to infrared waves, then we have this itty bitty little area here of visible light. So in this box, that's the waves that we can see. So that makes our rainbow of colors. Then as we keep moving over, the waves get closer and closer and closer and closer together as we go from UV waves, X-rays, gamma rays, and here we have high energy, we have high frequency, so it occurs lots in that amount of time, and we have short wavelength. So remember that this here from crest to crest or from trough to trough is the wavelength, and as from those tippity tops, those crests, as it comes closer together, you have a shorter wavelength. As it comes closer together, you get a higher frequency, more occurring in that set amount of time. So this is really interesting for us because we see different rays that can cause these changes in the nuclei to occur. The ones on this side have higher energy and they are more dangerous for us. They do cause more nuclei changes. So let's look at these. Oh, and by the way, you can look in your textbook. There's this really cool 2-page section talking about all the awesome scientists that helped to find out about these X-rays and helped to find out about this radiation and some really neat images of what they look like at first. All right, so what are these isotopes? So remember that a neutral atom has the same number of protons as it has electrons. So the electrons barely contribute to the mass of an atom. The mass of the atom, that bulk comes from the protons and the neutrons. The electrons have almost no mass. So the mass is the protons plus the neutrons. Now, we also know that electrons move from atom to atom, but they don't contribute to that mass. Protons are not able to move out of an atom, so only the electrons move. Please take note of that. So, thus, if we want to change the mass, we change the neutrons. So when the number of neutrons changes, we call this an isotope. So isotopes, here's a great definition, are atoms of an element that have the same number of protons, but a different number of neutrons. When we write isotopes, we do write them a little bit differently, and we call this the nuclear symbol. So what does the nuclear symbol look like? Well, it has the chemical symbol, so we've got the O, has the atomic mass, but now the mass is going to be at the top. The mass is on the above left, and the atomic number on the below left. So if we have oxygen, oxygen has 8 protons, and it has the protons plus the neutrons equals 16. So how many neutrons would oxygen 16 have? Well, the number of neutrons would be 8 plus 8 equals 16. So here, the oxygen O symbol, chemical symbol with the atomic mass on the top now and the atomic number on the below left. So if you were to write this, we would say oxygen 16 because oxygen can occur with different numbers of neutrons. So oxygen 17 then would have 17 at the top and 8 at the bottom. So this again is the protons. Here we have the protons and neutrons. So how many neutrons would you have? In this case, 9. And in oxygen 18, you would have 18 is protons plus neutrons. And if you have 8 protons, you must have 10 neutrons. Interesting. So sometimes we have these different numbers of neutrons because these nuclei are said to be unstable. Sometimes different isotopes are more stable than others. Sometimes you have a few isotopes that are stable and one that's unstable, or all of them are unstable, or all of them could be stable. But when they're unstable, they are likely to do something called decay. So they lose energy when they emit radiation, and this continues until the nuclei is stable. So this will happen over and over and over again until it's happy and stable. And sometimes, actually usually, the element actually changes into a different element. So this is one of those rare cases where it's okay for that element to change into something else. You didn't mess up. You did the right thing. So here I give you a little spot to put a definition of radioactive decay in your own words. We'll check up on what you put in class next day. And in this, in your textbook, BC Science 10 textbook, you'll see figure 7.7, and it looks a little confusing, so I wanted to go over it with you. Figure 7.7 shows us how uranium is an unstable element. It undergoes 14 different radioactive decay steps before it forms a stable, non-radioactive atom of lead-206. So, here we have uranium at the top. This is uranium, and it says uranium-238. And we can see here that the atomic number for uranium, if you follow the line here, the atomic number is 92, and the atomic mass is 238, so we're going to have 238 and 92. And this is going to change all the way down. So we have 1, 2, 3, 4, 5, 6, all the way 14 times into lead. And lead here has a mass number of 206, and it has an atomic number of 82. So that's what it's changing into there. That's how you would write, even when the numbers get really big, you still put the mass number on top and the atomic number on the bottom left. Carbon is another isotope that you may have heard of lots. You have carbon-12 and it has 6 protons. There's also carbon 13, still has 6 protons. There's also carbon 14 with still 6 protons. So again, just the number of neutrons are changing. There is an awesome table in your textbook on page 293 that compares these different isotopes. Well, I hope you are feeling like you sort of are getting to know what is going on with radioactivity. We will be practicing this more in class tomorrow and then looking at the differences between alpha, beta, and gamma decay.